Hello everyone. In this video, we are diving deep into the world of rheology, the study of how rocks flow and deform. If you are studying geology, structural geology, or just curious about the dynamic nature of our Earth's crust, this is for you. I am Namrata Biswas and I will explain everything from strain rates to histoplastic behavior in this video. So the word rheology comes from the Greek word rheos, meaning stream or flow. In geological terms, rheology is the science of the formation and flow of Earth's material. It's all about understanding how rocks behave under different conditions of stress, temperature, and time. For example, in this picture, we have the glacier. Now here we see the mass of ice and how it flows and forms different type of structures. In everyday uses, we can also take the example of using a tomato ketchup and things like that. Now, let's move on to the next slide. So, the geological strain rate is a fundamental concept in rheology. It refers to how fast a rock accumulates strain over time, essentially the change in shape or length per unit time. There is also shear strain rate, which focuses on how material layers slide past each other. This is critical in fault zones and ductile shear zones. The formulas are given in this slide. Now, if we look at the types of rheology, there are three main types. The elastic rheology, where deformation is recoverable like a spring. The viscous rheology, where deformation is permanent and time dependent, just like the flow of honey. And the plastic rheology, where the deformation happens once a stress threshold is passed, like molding of clay. Geologists use tools like the donut apparatus to simulate these conditions in the lab. Here we have different types of experiments like the axial compression where the sigma 1 is parallel to the axis, the axial tension where sigma 1 is perpendicular to the axis, and the tensile strength test. Now let's look at the ideal elastic behavior first. Elastic materials return to their original shape once the stress is removed and the deformation is proportional to the applied force. If we look at the graph A, this shows the linear relationship between the stress and the strain. The slope here is E or the Young's modulus, or it can be the shear modulus or the spring constant. This follows the Hooke's law, where sigma is equal to E into E, where the first E represents the Young's modulus and the E represents the strain. The straight line implies the instantaneous reversible deformation. In figure B, we have a simple spring system with stiffness K1. When the force is applied, it can be written as F equal to K1 into delta X. This is the ideal representation of a pure elastic behavior. There is no time dependence. The deformation occurs instantly upon loading and disappears upon unloading. The stress versus time graph in panel C shows a triangular loading cycle. It where the stress increases from 0 to a peak at around 2 seconds. It is held constant briefly between 2 to 3 seconds and it decreases back to 0 between 3 to 5 seconds. The strain versus time curve responses exactly following the stress curve. It increases proportionally with stress and decreases immediately when the stress is removed. No hysteresis or delay is observed. It is typical of elastic behavior. The elastic deformation occurs in rocks under low stress and short time For example, seismic wave propagation. It is important for understanding the earthquake energy stored and released. This diagram represents the ideal viscous behavior, a fundamental rheological model for materials that flow continuously under stress, like honey, magma, or rocks in the mantle over geological timescale. In figure A, there is the graph for stress versus strain rate. There is linear relationship with the slope. It is to be noted that here the Newton's law of viscosity is followed and the stress is proportional to the strain rate, not the strain. In figure B, we have the dashpot. The system is a piston in a viscous fluid. The force depends on how fast the piston moves. No deformation occurs unless the force is applied over time. And this dashpot is used as the mechanical model for the ideal viscous behavior. The stress versus time curve in figure C shows a step function of stress where the stress is applied at t equal to 1, held constant until t equal to 2 and removed after t equal to 2. The strain versus time curve shows that the strain increases linearly while the stress is constant between T1 to T2. Once the stress is removed, the strain stops and increasing but does not recover. So the strain here is permanent. No instantaneous deformation is observed. The deformation occurs only while stress is present. This describes how the ductile flow in rocks under long-term tectonic stress takes place. It is essential for understanding the mantle convection, rock creep, and glacial flow. Let's understand the ideal plastic behavior. In figure A, the vertical axis shows the shear stress sigma f or force F. The horizontal axis shows the strain rate. Once the yield stress sigma yield is reached, any amount of deformation can occur without any increase in stress. This is a characteristic of perfectly plastic materials where stress remains constant beyond the yield point. In figure B, we have a friction block. This block resists the motion due to static friction up to a yield force sigma yield. Once the applied force F exceeds sigma yield, the block slides with constant force, regardless of how much movement it undergoes. In figure C, we have how the stress is applied over time. It initially increases linearly from 0 to 2, held at constant at sigma yield for 2 to 3 seconds, and then it decreases back to 0 in 3 to 5 seconds. And in D, it shows the material's response to the applied stress. As long as the stress equals to sigma yield, any slope is possible. This means that the material can deform at any rate depending on conditions. Different lines show here different possible strain rates under the same yield stress. So here we can also see the strain is non-recoverable. Now here are some key elastic properties of rocks and their interrelationship, which is crucial in rheology. The first one is the Poisson's ratio, which is the ratio of lateral contraction to axial extension. As shown in the figure in the right side, if there is extension in two sides, there is the contraction on the other side. So this the typical value of Poisson's ratio in rocks is around zero point 0.1 to 0.35. This indicates how volume changes under stress. The Lamis constant is 1 of the two Lame parameters in elasticity theory. The other one is the G or the shear modulus. It is used in stress-strain relationship for isotropic materials. The shear modulus G in terms of lambda and the Poisson's ratio can be written like this here. It describes how a material resists the shape change at constant volume. The special case where the Poisson's ratio is equal to 0.25, then the shear modulus is equal to the Lame's constant. Under this condition, the five independent elastic constants reduce to four. This simplification is called the Poisson's relation. The Poisson's number is the reciprocal expression of the Poisson's ratio. Here, the relationship between the Young's modulus and other constants are also given. The typical range of Young's modulus in rocks is 1 gigapascal to 100 gigapascal. Now, in nature, we don't see materials behaving in ideal, elastic, viscous, or plastic behavior. Usually, there are combinations of these three types of behaviors. In complex or combined rheology, we will look at different combinations of the fundamental types of rheology. This diagram illustrates the behavior of a Kelvin viscoelastic material, a mechanical model that combines the elastic and viscous elements in parallel combination. It explains how such materials deform under load with time-dependent behavior and partial recovery. Let's break it down panel by panel. In figure A, it shows in the top part the that over a long period, the strain increases gradually and becomes linear with time under constant stress, indicating the viscous flow dynamics. In the bottom part, right after the stress is applied, the material behaves elastically, resisting deformation. So the stress is proportional to the strain rate. The Kelvin materials delay their full deformation, unlike ideal elastic ones which respond instantly. In figure B, it consists of a spring, which is the elastic component, and a dashpot, which is the viscous component, arranged in parallel combination. When force F is applied, both spring and the dashpot resist together. The spring wants to deform instantly, but the dashpot delays this deformation depending on viscosity. In figure C, the stress is applied instantly at time T1, held constant until T3, and then removed. This is a step function perfect to test time-dependent material response. And in figure G, the deformation begins gradually after the stress is applied, not instantly. The strain increases non-linearly during the stress period 1 to 3, then decreases gradually when the stress is removed, partially recovering due to the elastic nature. So here, no instantaneous jump in strain is observed. The dashpot resists the initial deformation, but there is also no full recovery because of viscous loss. This diagram represents the Maxwell model of viscoelastic behavior, which is ideal for describing materials that have both elastic and viscous responses, but with immediate elastic deformation and permanent viscous flow. If we look at figure B, it is composed of a spring, which is the elastic element, and a dashpot, which is the viscous element, and they are arranged in a series combination. When a force F is applied, the spring stretches immediately, but the dashpot deforms gradually over time, modeling the creep or permanent flow. Now, if we look at the panel A, it shows the response characteristics. The top graph shows a combination of elastic and viscous responses. The total strain increases over time with different curves for increasing viscous contribution. And the bottom graph, it shows the purely viscous materials, and there the stress increases linearly with strain rate. It shows the viscous part of the Maxwell model. If we look at figure C, it is the stress versus time curve. Here, a step load is applied and it stays constant between T1 and T2. Then it is removed. It is perfect for observing the sweep and recovery behavior. And in figure D, where this represents the strain versus time curve, it shows that at time t equal to 1, the instantaneous elastic deformation or the vertical jump is observed. From T1 to T2, the continued increase in strain is due to the viscous flow. At T equal to 2, the stress is removed and the elastic strain instantly recovers. The strain drops, but the viscous strain remains permanently. The Maxwell materials don't return to the original shape after stress is removed. They show irreversible deformation. The Maxwell model helps explain the ductile behavior in rocks over long geologic timescales or soft metals and polymers under slow loading, whereas the Kelvin model is ideal for materials like rocks or polymers that show creep under load but attempt partial recovery when unloaded. If we look at the elastic plastic rheology, it is a combination of elastic and plastic deformation behaviors, often used to describe the response of real-world rocks and metals under stress. In figure A, the stress remains constant once the yield stress is reached. This implies that once yielding starts, the strain rate can vary, but stress stays at the yield level. It represents the perfect plastic flow after initial elastic resistance. In figure B, a spring or the elastic element is in series combination with a slider or a friction block, which is the plastic element. The spring deforms elastically until the yield stress is reached. After that, the friction block moves, allowing the plastic or permanent deformation at constant force. In figure C, a cyclic stress pattern is applied. It ramps up to sigma yield by T2, held constant from T2 to T3, and then it decreases back to zero. This is a standard test for elastic plastic behavior. In figure D, the strain increases elastically or linearly until time T2 is reached, where the sigma is equal to the yield stress sigma E. Between T2 and T3, the plastic deformation occurs, where the slope can be arbitrary, which means that the strain rate is not fixed. After T3, the stress is removed. The elastic part is recovered instantly, but the plastic strain remains as the permanent deformation. This model is essential for understanding the rock deformation, fault zone mechanics, and materials under tectonic stress. Now let's look at the viscoplastic behavior. It is a model combining the plastic deformation with viscous flow, often used to describe rocks and materials that exhibit time-dependent permanent deformation after reaching a yield stress. Here in figure 1 we have the stress versus strain rate curve. Below the yield stress sigma yield, there is no deformation observed, or the material behaves rigidly. Once the stress exceeds sigma yield, the deformation begins and the stress strain rate curve becomes linear. The slope 2 eta or a constant K2, this controls the rate of flow. Once yielding starts, the rate of deformation depends on the viscosity or the resistance to flow. Now, in figure B, a friction block, which is the plastic element with yield threshold, is in parallel combination with a dashpot, which is the viscous element. Below the yield stress, there is no motion, since there is resistance from both of them. But above yield, the dashpot activates and the material begins the viscous flow. It captures rate-dependent plastic flow. In figure C, we have the stress versus time curve where a loading-unloading cycle is applied. There is linear increase to sigma yield from 0 to 2 seconds. It is held constant between T2 to T3 and it decreases back to 0 from 3 to 5 seconds. The classic input for analyzing the time-dependent flow. In figure D, we have the strain versus time curve, where from 0 to 2 seconds there is no significant strain, where stress is less than the yield point. From 2 to 3 seconds, once the yield stress is reached, the strain increases at a rate controlled by the viscosity, and after 3 seconds, when the stress is removed, the strain remains constant or there is permanent deformation. Since and hence there is no elastic recovery. This model is useful in geology for fault script, ductile shear zone, and deep crystal rock flow where viscous drag and yield conditions interact. A classic example of complex rheology in real life is the earthquake mechanism, where we can see the elastic plastic behavior. So the earthquake occurs along the Wadati-Benioff zone at the subduction zone where a oceanic crust is going under the continental crust. Now, the oceanic crust as it is moving under the continental crust, initially there is a resistance from the slab. So, initially there the strain increases linearly, but there is no deformation. So it behaves as an elastic material. But once there is the yield stress reached, it ruptures and earthquake occurs. So here we can observe the plastic deformation where the strain is non-recoverable. Now, the earthquake mechanism is a much complex process, but this is a simplified version of it. This graph shows the concept of strain hardening and strain softening, which is an important concept in material deformation, especially relevant to rocks, metals, and geologic materials under stress. It plots the stress versus strain in y and x-axis. Here, the elastic region is denoted by the black line. This is the initial linear portion where stress and strain are proportional. Here deformation is reversible. It removes the stress and the material returns to its original shape. It is governed by the Hooke's law. Now, when the yield point is reached, beyond this point, the material undergoes permanent deformation. The behavior diverges into three possibilities. The red line represents the strain hardening. Here, after yielding, the material becomes stronger with increasing strain. The stress continues to increase with strain. This is common in metals and some ductile rocks under low strain rates. New dislocations or microstructures resist further deformation. The no hardening or the perfectly plastic blue line, here the stress stays constant after the yield point. The material deforms continuously under the same stress, which is perfect plastic behavior. It is seen in simplified models and idealized geological simulations. The green line represents the strain softening, where after yielding, the stress decreases with increasing strain. It indicates material weakening. It is common in brittle rocks, fault gouges, and fault zones. It is associated with localization of strain and potential failure, example, fault slip or shear bands. This diagram shows the generalized creep curve. The first stage of creep involves the elastic deformation, where it occurs instantly when the stress is applied. It is reversible. The material returns to the original shape if stress is removed. It is marked by the steep linear slope near the origin. The second one is the yield stress. Here, this is the transition point between elastic and permanent deformation. Once it is surpassed, creep begins. The strain continues to increase even if the stress stays constant. The third one is the primary creep or the decelerating creep. Here, the strain increases quickly at first, but the rate slows down. The internal material structure adjusts to the applied load. It often involves strain hardening, where resistance increases. The fourth one is the secondary creep or the steady state creep. Here, the strain rate is constant. It appears as a straight line, the longest phase in most materials. It is critical in geological timescales as it represents the stable ductile deformation in deep crust or mantle. The tertiary creep or the accelerating creep, here the strain rate accelerates rapidly. The microstructural damage accumulates. Example, the crack propagation, grain boundary sliding. It leads to failure or rupture. And the final one is the rupture point, where the material breaks or fractures. The total strain has become unsustainable for the material. Now, why is it important and how we can relate it to real life problems? The elastic part represents the Earth's crustal response to small stress. The primary creep is the adjustment phase in faults or folds. The secondary creep can explain the long-term ductile flow of rock. The tertiary creep can explain the pre-failure indicators in landslides or earthquakes. And the rupture represents the earthquake or fault slip event. The intrinsic factors affecting rheology are the elasticity, viscosity, rigidity, compressibility, and effective viscosity. The extrinsic factors affecting rheology are the temperature, confining pressure, pore fluid pressure, strain rate, and time. In the next few slides, we will look in more detail at the extrinsic factors. This graph represents the effect of confining pressure in the behavior of rock. Here, the example of deformation studies done on Crown Point limestone is taken. The x-axis represents the strain in percentage and the y-axis represents the differential stress in bars. Each curve corresponds to a different confining pressure from 200 to 1800 bars. Now, at low confining pressures, 200 to 400 bars, for example, the rocks show brittle behavior. There is steep initial rise, the peak stress is reached, and there is sudden drop or the post-peak failure. The drop in stress indicates fracturing or brittle fracture. The little strain accommodated before failure indicates the low ductility. At intermediate pressures around 600 to 800 bars, the peak stress is higher. The post-peak drop is less severe, suggesting the transition behavior between brittle and ductile. Some strain softening is happening, but the rock does not fail catastrophically. At high confining pressures around 1300 to 1800 bars, the rocks become more ductile. High stress is sustained. There is no sharp stress drop. Instead, a flattening curve or slight hardening is observed. Rock deforms continuously without fracturing and it exhibits ductile flow. To summarize, the increasing confining pressure strengthens the rock, which is indicated by the higher peak stresses. It also suppresses the brittle failure and promotes ductile deformation. This behavior is fundamental in structural geology, especially for understanding the crustal deformation, fault mechanics, and tectonic stress regimes. This graph shows the relationship between confining pressure and strain before faulting for various rock types, essentially measuring how ductile a rock becomes before it fractures under increasing pressure. The x-axis represents the confining pressure in megapascal and the y-axis represents the strain before faulting in percentage, which is a measure of ductility. As confining pressure increases, all rock types show increased ductility. They can deform more before breaking. However, the rate and extent of this increase differ significantly by rock type. The more ductile rocks like shale and sandstone exhibit the highest strain before faulting at high pressures. These rocks become very ductile under confinement, tolerating up to 20 to 25% strain before failing. The moderately ductile rocks like limestone and anhydrite show intermediate ductility. They deform more than harder rocks, but less than the shale or sandstone. The quartzite and slate show the least ductility. Even under high confining pressure, they fail at low strain levels, meaning they are more brittle overall. The confining pressure suppresses the crack propagation, promoting a plastic deformation. The rocks with clay content or porosity, like shale or sandstone, accommodate deformation better. The dense crystalline rocks, like quartzite or slate, resist the flow and fail earlier. And this is the reason why this type of behavior occurs in different rocks. The more ductile before breaking the rock is, the more strain can be accommodated in it and the less prone to brittle fracturing it will be. This graph is key for understanding the rock mechanics in tectonic environments, fault zone behavior, and reservoir stability. From This graph shows the effect of strain rate on the stress strain behavior of rock at a constant temperature of 500 degrees Celsius. It helps visualize how fast deformation or strain rate influences rock strength and ductility. The x-axis, like before, represents the strain in percentage and the y-axis represents the differential stress in megapascal. Each curve corresponds to a different strain rate in second inverse, ranging from fast deformation around 4.0 into 10 to the power minus 1 second inverse to slow deformation around 3.3 into 10 to the power minus 9 second inverse, which is at the bottom. At high strain rate, it requires higher stress to achieve the same amount of strain. The material appears stronger but also less ductile. It deforms less before reaching the high stress. For example, around 4 into 10 to the power minus 1 second inverse, there is the steep curve and high stress. At low strain rate, it requires less stress to deform. The material is weaker but more ductile. It allows more strain over time. For example, the 3.3 into 10 to the power minus 9 second inverse, it shows flatter curves and lower stress. Strain rate sensitivity is a hallmark of viscoelastic and viscoplastic materials. At constant temperature, a higher strain rate inhibits dislocation motion, builds up stress faster, and leads to brittle or less ductile behavior. At lower strain rate, it allows time for relaxation, diffusion, or creep. It promotes ductile deformation. To summarize, if the strain rate is more, the stress is more, but the ductility is less. And if the strain rate is less, the stress is less, and the ductility is more. It is important for modeling the fault behavior, rock creep, and deep crustal flow. Now let's look at this parameter. These two graphs illustrate the effects of pore fluid pressure and temperature on the deformation behavior of rock, specifically between limestone and quartzite. Both are critical controls on rock strength in the Earth's crust. The left graph represents the effect of pore fluid pressure on limestone. Here, the confining pressure Pc is equal to 70 megapascal is held constant. The curves correspond to different pore fluid pressures from 0 to 70 megapascal. The y-axis represents the stress in megapascal and the x-axis represents strain in percentage. As pore fluid pressure increases, the differential stress at failure decreases significantly. High pore fluid pressure reduces the rock strength, promoting the earlier failure at lower stress. At 70 megapascal, the rock essentially fails almost immediately with very low strength. It can be explained by the pore fluid pressure. As the pore fluid pressure reduces the effective normal stress, sigma effective can be written as sigma total minus pore fluid pressure. This weakens the grain contact, encouraging fracture or fault slip. At high pore pressure can trigger earthquake and promote brittle fracture. It is common in overpressured sedimentary basins, subduction zones, and hydrofracture settings. Now, if we look at the right graph, there is the effect of temperature on quartzite, dry and wet. The deformation behavior of quartzite at increasing temperatures is observed at 400 degrees C, 700 degrees C, 900 degrees C, and 950 degrees C. Here, as temperature increases, the strength of quartzite decreases. The peak stress or the yield strength sigma y is highest at 400 degrees Celsius. The ductility increases at higher temperatures where the curve is more flattered and extended. At 950 degrees Celsius or the wet quartzite, the rock is dramatically weaker and flows readily, very low differential stress. Here, at elevated temperatures, it activates the dislocation speed and diffusion flow. It reduces the internal resistance, making the rock more ductile. Here, the water or the wet condition greatly enhances the ductility by reducing the friction at grain boundaries. It explains the deep crustal flow in metamorphic terrain, where wet conditions in subduction zones promote ductile deformation rather than brittle fracture. This table summarizes how the environmental parameters affect the rheological behavior of rocks as we have discussed so far. This is the representative stress strain curve and it shows how brittle and ductile rocks behave. The brittle rocks fail by fracture at less than 3 to 5% of strain and the ductile rocks are able to sustain under a given set of conditions around 5 to 10% of strain before deformation by fracturing. These are some of the references I have used. Thank you for listening.